So the objective of today's lecture is we will study in detail about the scattering loss and types of scattering loss. Okay, and then how I can reduce the scattering loss. So this I had shown this diagram yesterday. So remember again, scattering loss are of two types: linear scattering, non-linear scattering. Linear scattering is again of two types: Rayleigh and mean scattering. Non-linear scattering is again of two types: stimulated Brinall scattering or stimulated Raman scattering. RAMAN भी लिखते हैं, RAMEN भी लिखते हैं. Okay, since it's a name of the person, so the spelling does not matter. But mostly RAMAN, Raman we use in this particular site which I took from internet. Okay, so here it is REMEN. But if you write MEN, then also no problem. So now we will study all these four types of scattering in details. Okay, so linear scattering. Now linear scattering, here it is saying that it also causes absorption of light energy. Okay, but it is not an absorption loss. Now why? Absorption loss, the light was absorbed by the impurity, and in scattering we have seen in the initial definition that the light bounces back from that particular impurity. Then why I am calling it as also absorption loss? So let us see why linear scattering, or you can say scattering, is almost similar to absorption loss, but there is still some little bit different. So what is linear scattering? In linear scattering, the power is transferred linearly to another mode, and in this process tends to result in the attenuation of signal as the transfer of power takes place from one mode to another mode. Now that mode may be leaky mode. So due to this leaky mode, what happens? The light escapes from the core into the cladding. Now when all these transformation of light from one mode to another mode, and that mode is a leaky mode, or you can say that mode is escaping from the core of the fiber. Remember this, I had highlighted yesterday also, there is no change in the frequency. Okay, so that makes it linear scattering. So linear scattering means the light is scattered, it bounces back, it leaves, escapes the core and enters into the cladding, but there is no change in the frequency. Okay, so that's why we call it by the name of linear scattering. Now linear scattering is of two types: Rayleigh scattering and mean scattering. Now let us see what are the causes of these. So let us start with the Rayleigh scattering. Now as I am saying this, you listen, but then afterwards actually everybody forgets. It's not possible to remember. So if you are making or writing notes or noting down the keywords, it will be useful. Now why Rayleigh scattering is caused? Rayleigh scattering is caused due to two reasons. First is inhomogeneities in the composition of the core. Okay, so as such there should be a homogeneous structure of the core when I am fabricating it, but yes, there might be some irregularities during the fabrication process, and there are inhomogeneities in the composition of the core, and then the refractive index fluctuation. Okay, so jitna refractive index hona chahiye tha, okay, due to all those dopants and all. See, remember, it's a very complicated process. We are collecting the soot on either on the structure or inside a particular. Okay, so initially inside the deposition में हम लोग dopants डालेंगे ताकि core का deposition हो. बाद में we will add the dopants ताकि वो cladding का deposition हो जाए. Okay, but then there might be something might go wrong, and then the deposition, the preform that I fabricate, it might have a non-uniform deposition of the soot, and then when I introduce the preform in that furnace, melt it, and I try to draw the fiber. Okay, so obviously jo refractive index hai, it might vary when I'm drawing the fiber in the drawing tower. So these are again the two reasons, something which happens in the fabrication process. It is not that the user or the person who is laying the fiber, उससे भी losses होते, but this loss is not in our hand. So only by improving the fabrication technique, I can reduce Rayleigh scattering. So the inhomogeneities and the refractive index fluctuation, it should be low as possible. So if I want to reduce Rayleigh scattering during the fabrication of the fiber cable, okay, fiber, these two things should be low. Now what happens in Rayleigh scattering, this we will see. So for glass fiber, the foremost type of scattering is Rayleigh scattering. Okay, so what happens in Rayleigh scattering is, with this process, atoms or other particles within the fiber, they absorb the light signal. Just pay attention to this particular line. हमने absorption already पढ़ा है, but now in scattering also we are using the term absorption. Okay, so what actually happens is, the particles within the fiber, they absorb the light signal and instantly re-emits the light in another direction. जो actual absorption loss था, उसमें क्या होता था, particle जो है, if I use in Hindi, वो खा जाता था. Okay, that signal means the signal light energy was converted into heat energy. So finally my light signal is lost. So here the particle, what it will do, it will initially absorb the particle and re-emit it in another direction. So it is not keeping it with itself. Okay, so in this way, the Rayleigh scattering appears very much like absorption, but it absorbs and redirects the light so quickly. So that's why it is considered as scattering. So that's why I don't call or categorize Rayleigh as an absorption loss, but since it releases the light in a different direction, I call it as a scattering. And that process happens very quickly. Now, Rayleigh type scattering in glass is the same phenomena that scatters light from the sun in the atmosphere, thereby giving rise to a blue sky. These are the two links of videos which I will show you. So suppose here there is, this is the diagram in your book. So here there is one external impurity particle or some inhomogeneities that is present over here. So when the light is incident on this, okay, so the light bounces back and it re-emits the light in different direction. Okay, so it can be this way, one light can be this way, okay. And finally, this one might be propagated, but you can see the other ones are lost. Okay, now continuing with this slide is important. In commercial fibers operating between 700 nanometer and 1600 nanometer, the main source of loss is Rayleigh scattering. Rayleigh scattering is the main loss mechanism between the ultraviolet and infrared region. Okay, this one in blue is important. That's why I have highlighted it with a blue color. Rayleigh scattering occurs when the size of the density fluctuation or the foreign particle, or you can say the defect, is less than 1/10 of the operating wavelength of light. मेरे fiber के अंदर impurity है. Okay, so with that impurity, the size of the impurity matters. Suppose I have one impurity present. So that density of impurity, if it is less than 1/10 of the operating wavelength, so if it is less than lambda by 10, suppose this is the density, which I'm calling it as D, suppose, okay, that is less than 1/10 of the operating wavelength, or jo defect hai, that size is less than 1/10 of the wavelength, then Rayleigh scattering occurs. If this density is greater than lambda by 10 or 1/10 of the wavelength, then the scattering that happens is called as me scattering. So Rayleigh और me scattering के बीच में difference यही है कि particle का size कितना है. Okay, so if the size, or you call it as the defect, okay, whatever fluctuations, okay, you can give whatever name you want, that density, if it is less, means iska size kam hai. So that scattering is called as Rayleigh scattering. So please remember how, if I want to differentiate what is actually Rayleigh scattering, in both some impurities there, the light is striking and it is scattering in a different direction. So as the wavelength increases, the loss caused by the Rayleigh scattering decreases. Okay, so this is one diagram which you will find in the book. So here you can see the light is scattering. So there is some density fluctuation takes place and the light gets scattered in a different direction. Okay, so only thing I can reduce this scattering is by having a proper fabrication method. Now coming to me-scattering. Okay, so me-scattering is caused by three reasons: irregularities at the core and cladding interface, core diameter fluctuation. If I say कि 8 micrometer diameter है तो कहीं पे कुछ तो problem हो जाएगा. Okay, so the area might be less, it might be 7.8, 7.9 or 7.5. Okay, and then again problem starts. Bubbles present in the core. Again, all these are caused due to improper manufacturing process. Okay, so I hope you remember कि what were the causes of Rayleigh scattering? Inhomogeneities in composition, refractive index fluctuation, and when I talk about my scattering, irregularities at the core cladding interface, core diameter fluctuation, bubbles present in the core. Okay, so these are also the result of improper fabrication technique. Now, when I'm talking of the size of the defect, if the size of the defect is greater than 1/10 of the wavelength of light, the scattering mechanism is called as me-scattering. Now, me-scattering caused by these large defect in the fiber core, it scatters the light out of the fiber core. However, in commercial fiber, the effects of me-scattering are insignificant. देखो क्या-क्या defect था? Irregularities at the core cladding interface, core diameter fluctuation, bubbles present in the core. So now if I have a proper fabrication technique, why there will be core diameter fluctuation? अगर 8 micrometer का core है तो वो हो सकता है. हाँ, might be some bubbles are present because due to that oxyhydrogen torch, which I cannot avoid. Okay, so that's why the effect of me-scattering is less in commercial fibers. Okay, because we don't manufacture fibers having very large defect. Okay, so this is pointing out that it is a large defect. Jabki Rayleigh scattering mein, it is actually a small defect. Okay, now small defect might be there during the manufacturing technique, but large defect usually are avoided. So Rayleigh scattering, that's why that sentence was there. Rayleigh scattering is one of the significant loss mechanism that happens in the fiber. Now, how I can reduce my me-scattering is removing imperfection due to the glass manufacturing process. Yes, so I can design a proper way of manufacturing the fiber, carefully controlled extrusion and coating of the fiber. देखो core cladding interface में irregularities है. So the moment I draw the fiber from the tower, fiber drawing tower, we first apply an elastic coating. So वो अच्छे से लगाना है. Otherwise, if some contaminants are added during the very first coating of the fiber, then again there will be scattering. Increasing the fiber guidance by increasing the relative refractive index difference. Okay, so the refractive index of the core was changing. So suppose if it changes, so what I do is, what I keep is, when I design a fiber, core और cladding के बीच का जो relation है, that is the relative refractive index difference delta. I try to keep that value of delta large. So by trying to keep the value of delta large, जो core और cladding के बीच में जो relative index difference है, that increases. And then if there is some fluctuation in the refractive index of the core, that can be neglected because delta itself is a very small figure which is less than 1. So that was your category of linear scattering, which was Rayleigh scattering and me-scattering. The next category is your non-linear scatterings. Now it depends, here the approach is a little bit totally different in case of non-linear scattering. It depends upon the optical power input. Because of high optical power input, non-linear scattering increases. Now see, if input power is more than threshold power, PTH, there exists a non-linear scattering. So simply I cannot send any amount of power through the fiber cable. So there is always a threshold power. And if suppose the input power is exceeding the threshold power, then non-linear scattering happens. Now what happens is, due to this, the power flows in the backward direction, that is towards the source. Along with the power scattering, there is change in the optical light frequency. And due to this change in frequency, we get the name as non-linear scattering. If the frequency is changed, our output is not as desired. So as such, linear scattering is still tolerable, but non-linear scattering is actually not, because the frequency of the light signal changes. So now there are two categories of non-linear scattering: stimulated Brinall scattering and stimulated Raman scattering. Okay, both of which are usually only observed at high optical power densities in long single mode fiber. So SBS and SRS, this phenomena takes place in a single mode fiber. Actually, these scattering mechanism in fact give optical gain, but with a shift in frequency, so thus contributing to the attenuation for light transmission at a particular wavelength. Okay, since my input power was exceeding the threshold power and power was flowing in the backward direction, so if I actually measure the output power is more. Okay, so there is one formula to calculate the output power, and many other terms of fibers are also related. I'll give you that formula. Okay, so your output power is more. So you might feel, Are, acha hai na, without amplifiers, I am getting more output power. But since there is a change in the frequency, that is not accepted, and that's why there is attenuation of signal. So let us understand what is stimulated Brinall scattering. Here some new terms, new concepts will be there. अब तक हमने क्या देखा कि कोई impurity है, light उसको strike हो रहा है, and it is scattering in a different direction based on the size of that impurity or defects. I had Rayleigh scattering and my scattering. Now here, when I'm talking of non-linear scattering, it is totally a different approach of understanding. So pay attention, okay, because these points are a little bit confusing when we try to understand stimulated Brinall scattering or stimulated Raman scattering. So read a while after we finish the lecture, or after you finish your IA, please revise. Otherwise, ये दोनों जो scattering है, SBS and SRS, it is not easily understood by the student. Okay, so stimulated Brinall scattering is the modulation of light through thermal vibration within the fiber. So this is one new term that is coming. So what happens in SBS is, the glass particles which are there, it starts vibrating or it starts oscillating. Okay, and due to that, modulation takes place. So modulation frequency for the scattered light, what it does, it separates the incident light into upper and lower sideband. The incident photon produces a photon of acoustic frequency as well as a scattered photon. वो क्या हो जाता है? See, the glass particle, okay, it starts vibrating or starts oscillating. Now you have seen an engine. When the engine runs, okay, there is some vibration, okay, or you can call it oscillating. It is moving. We can hear a sound, okay, a humming kind of sound. So similarly, when the glass particle, it starts vibrating, there is an acoustic photon that is generated. Acoustic means that sound. Okay, so an acoustic photon is generated due to this thermal vibration. So what happens is, this produces an optical frequency shift which varies with scattering angle, because the frequency of sound wave, it varies with the acoustic wavelength. और ये acoustic कहाँ से produce होता है signal? Due to this vibration. The frequency shift is maximum in the backward direction, reducing to 0 in the forward direction, making SBS a mainly backward process. So this is in comparison with your stimulated Raman scattering. So stimulated Brinall scattering may that frequency shift is maximum in the backward direction, reducing to 0 in the forward direction. Okay, so backward and forward, I'm talking about the fiber. If this is the source, this is the receiver. I'm talking of this is the forward direction and this is the backward direction. Okay, so Brinall scattering is only significant about a particular about a threshold power density. So the optical power level at which Brinall scattering becomes significant in a single mode fiber is given by the formula. See, ऐसा नहीं है कि मैं मेरे पास फाइबर है, मुझे जितना इनपुट पावर देना है I will give and I'll expect कि हाँ ठीक है पहले से ही मैं ज्यादा पावर दे देती हूँ. Okay, if you are a small child and if you are a 22-year child, same amount of food we cannot give you. If you feel कि अरे चलो अभी सुबह से ही ज्यादा खा लेते ताकि पूरा दिन भूख न लगे, okay, so that is not possible. So similarly over here I cannot simply pump in any amount of power at the input. So there is some formula, okay, there is some threshold power at which, and if I exceed that threshold power, I definitely get Brinall scattering. So this is the formula to calculate the threshold power. And remember, SBS, SRS are both for a single mode fiber. So this is that particular formula. You can remember this formula. Right now, I'm not insisting because you don't have this portion in IA. So here D, lambda, alpha, delta T is there. So D is fiber core, lambda operating wavelength, alpha dB fiber attenuation, and delta T is the source bandwidth. Okay, in senior, it is there in my notes. Some data is given related to all these things. ये कभी exam में आया नहीं है, so I don't cover it in class, but I tell the students to prepare. So suppose they tell you to calculate the threshold power, then you can have this particular formula and all these parameters are there. So in the numerical, they will give you all these parameters and you have to remember this formula and you calculate the threshold power. So I'm not covering that question in class, but you can prepare it for the safety side. Okay, now coming to stimulated Raman scattering. Okay, so what happens in stimulated Raman scattering is it generates a high frequency optical phonon. In SBS, I was using photon. Now here an optical phonon is generated. Now what is an optical phonon? This is totally a new term. So I will just show you from Google. I hope you can see the page. So phonon का मतलब क्या है? SRS, it generates an optical phonon. अब तक हमने देखा था electrical photon is generated. Okay, similarly for light energy, an optical photon is generated. But now here in SRS, a phonon is generated. Now what is a phonon? So here I just took this, itna padne se hi you can understand. I hope you can see the Google page. Yes?
Yes, ma'am.
Okay, so what is a phonon? So just see a photon, which you have studied. A photon is a form of energy, but the phonon is a mode of oscillation. As I said in the last case also, thermal vibrations or oscillation happens inside the fiber. Okay, so phonon is a mode of oscillation that occurs in the lattice structure. Okay, so that oscillation, we are calling it as the phonon. A photon can be considered as a wave and a particle, which are physically observable entities. I can see a photon of any signal, but a phonon is a mode of vibration which is neither a wave nor a particle. Just read it once, and I hope that will clear ki phonon ko what actually I'm meaning by the phonon. since the particle starts vibrating or oscillating, okay, so that I'm calling it as a phonon. That vibration or oscillation, I'm calling it as a phonon. So it's just a mode of vibration. So I cannot say it is a wave, nor I can say it is a particle. Is this clear? What is phonon? Yes, Ritik, unmute kiya tha, means yes. Okay, so.
A phonon is neither a particle nor a wave.
Okay, so in SRS, it generates an optical, a high frequency optical phonon in the scattering process and is similar to SBS, except that the acoustic phonon is generated in SBS rather than the optical photon. SRS occurs in both the forward and backward direction in the optical fiber and has an optical power threshold up to 3 orders of magnitude higher than Brinall's scattering. Okay, so this is what is the difference between your SRS and your SBS. कि वहाँ पे it was a completely backward process. Okay, यहाँ पे the direction of propagation of light, it takes place in the forward and the backward direction, and the power threshold is 3 times the order of magnitude compared to the Brinall's threshold. So stimulated Raman scattering is an interaction between the light wave and the vibration mode of the silica molecule. SRS generates scattered light at a wavelength larger than that of the incident light. Optical, this is now the bending loss. I'll just try to absorption loss we have already studied, but I'll show you. It is just a 42 seconds video. Just see it. So it will be like a
Transformation of light into heat as it passes through a dense medium.
What I wanted to show you that particle was, when the light was striking, that red and those hydroxyl ions are there, the signal is lost. So it has been observed. Okay, now let us understand the Rayleigh scattering.
Rayleigh scattering. The elastic distribution of light in all directions, which is caused by interference with particles smaller than the wavelength of the light itself.
Animation so that you can feel okay how the light signal is lost. Okay, and I'll show you this video and then part 2 in the next class. So here many losses are covered. It's a 6-minute video, so just have a...
How easy is it to make a call today? You just have to think that you need to talk to somebody, and then you immediately call up your friend, and given that he or she answers your call, you can immediately talk to them. While all this information travels in no time, there may be situations in which information may be lost through the channel. Identifying these probable losses are important so that they can be minimized and the flow of communication occurs with minimum losses. Telephone signals, internet communication signals, and cable television signals all use optical fibers to transmit information from one place to another. These optical fibers tend to have some irregularities which create loss in the information signal. These losses are divided majorly into 5 types, and there are subdivisions to each type which will be discussed as we learn more about it. Before we discuss the type of losses, we need to know how we determine the losses. Now suppose you're saying something at one end of the phone and the other person is not able to hear you clearly. This shows that some signal is getting lost in the way. This loss of signal in the optical fibers is termed as attenuation. Attenuation is measured with the help of a formula which is given as the ratio of input optical power to output optical power over the length of the fiber L. Its unit is decibel per kilometer. Attenuation or loss in signal strength is caused in the fiber due to absorption losses, scattering losses, dispersion losses, radiative losses, and coupling losses. In this video, we'll be discussing absorption losses and scattering losses. First, we'll talk about absorption losses. An optical fiber is made up of either glass or plastic material. During fabrication of the fiber, there might be some impurities present in the fiber that can cause loss in the signal. This loss is called absorption loss. Here, the signal is absorbed and converted into other forms such as heat. The amount of loss that the signal incurs due to absorption losses depends upon the concentration of impurities present in the fiber. Absorption losses are further classified into intrinsic absorption losses and extrinsic absorption losses. Let's first discuss intrinsic absorption. In the optical fiber, the light-carrying particles are called photons. These photons, when interacting with the electrons that are present inside the fiber, are absorbed by the electron and raise them to a higher energy level. This results in a loss of light signal and is called intrinsic absorption. The next type of absorption loss is the extrinsic losses. While intrinsic absorption is caused by the metals that are fused with silica to make the fiber, extrinsic absorption is caused by the impurities present in silica. These include metals like iron, copper, cobalt, nickel, manganese, and chromium. They tend to absorb the optical signals. This is why their impurity concentration is kept less than 1% to achieve a loss level below 1 decibel per kilometer. And sometimes there might be some hydroxyl ions, or to say water vapors, present inside the cable fibers which might have remained during manufacturing. This also causes a significant loss in the optical signal. After absorption loss, we have scattering loss. Scattering loss scatters the signal inside the optic cable. Scattering loss is further divided into linear scattering and non-linear scattering. We know that inside an optical fiber there are different modes that carry signals. A condition in which a mode carrying an optical signal is scattered onto a different mode is termed as linear scattering. Linear scattering has 2 major divisions, Rayleigh scattering and Mie scattering. In Rayleigh scattering, the atoms inside the fiber absorb the light and then scatter it in a different direction. Although this appears like absorption loss, but here the light is scattered back, and this makes it different from absorption loss. Here's a fun fact. The scattering of the blue light in the atmosphere is also caused by Rayleigh scattering. Next, under linear scattering, we have Mie scatterings. They are caused by particles that are of the size of the wavelength of the scattered light. The optical signal, when it hits these particles, result in the scattering of light in the forward direction and is termed as Mie scattering. Now, coming to non-linear scattering, the optical power is transferred from one mode to another, either in the same frequency or different frequency. The direction of scattering can be forward or backward. Non-linear scattering is further divided into stimulated Brinall scattering and stimulated Raman scattering. In stimulated Brinall scattering, the strong optical signals inside the fiber are converted into acoustic signals. These signals travel backward and interfere with the incoming optical signals, causing a loss in signal strength. In the second type of nonlinear scattering, that is stimulated Raman scattering, the signal that has a shorter wavelength transfers its energy to the signal with the longer wavelength. This transfer of energy between the signals results in limiting the performance of the signal. Well, that's all about absorption losses and scattering losses. In the next
Yeah, I hope you that video was just a revision of what I had covered. So absorption loss and scattering loss, I hope it is clear to all of you. Yes or no?
Yes, ma'am.
Yes, ma'am.
Okay, good. So now I will not cover more today because we have